Okay, the last example I want to do is just a type of problem that does come up. It comes up occasionally in calc when you're doing integrals, but really this is just a way to better understand what kind of is happening with a trig function. So here's what we're going to do. They're going to be kind of weird problems. We're going to simplify tangent of sine inverse of x over 2. So I like these problems because they really get into what it means when we talk about an inverse trig function, and it helps us just kind of make sense of problems. So first of all, let's take a look at this part, sine inverse of x over 2. This is an angle, which we could just call theta. Notice up here, the range of an inverse trig function is an angle. So that means that sine inverse of x over 2 spits out an angle. Now we don't really know what the angle is because we don't know what x is, but we could still make sense of this problem. So what I'm going to do is I'm actually just going to draw a triangle now. I don't have to necessarily use a unit circle. You could use a unit circle if you like, but I'm just going to make a triangle. And I'll call that theta. So this theta right here is actually sine inverse of x over 2. Now, in order for this to actually be true, that x has to be the opposite side, and that 2 has to be the hypotenuse, because that's the definition of sine. And so really what this problem boils down to is I'm now trying to find out what tangent of theta is. Well, tangent of theta is opposite over adjacent. So that means I need to figure out what the adjacent side is. Using the Pythagorean theorem, we would end up with the square root of 2 squared minus x squared, or just 4 minus x squared. And so that means that tangent of theta would end up being opposite is x, the adjacent side is the square root of 4 minus x squared. And so then going back to the original problem, the answer is this is just x over the square root of 4 minus x squared. So the reason that this problem does come up is because it takes a trig expression, which isn't always useful and is sometimes harder to manage, and it turns it into, this is now an algebraic expression. And that's why it's used in calculus. Sometimes it's easier to work with the algebraic version, and then you can kind of work backwards at the end of the problem to get back to trig. Let's try another one. Let's do cosecant of tangent inverse of x. So once again, keep in mind that this is just an angle, which I could call theta. So let's create our triangle based on these requirements. Tangent is opposite over adjacent. So I have my opposite is x, and I'll just say it's x over 1. And so then I need the hypotenuse. Hypotenuse is going to equal the square root of x squared plus 1 squared. Now cosecant is the reciprocal of sine. So that means it's going to be the hypotenuse over the opposite side. And so that tells me that cosecant of theta in this case is going to be the square root of x squared plus 1 over the opposite side, which would be x. So that means that cosecant of tangent inverse of x just equals the square root of x squared plus 1 over x. And that would be my final answer. So once again, these problems are not really going to be super common, but it is important to be able to do them because this illustrates a couple of key facts about trig. One thing I really like about this is it draws so much in. I mean, we did a cosecant, so we had to remember that. We had to use triangles. We had to use the Pythagorean theorem. So there's a lot of good math happening here, and I like how it connects all of that stuff. In terms of applications, it does come up in calc, but it's sort of a rare application. My bigger reason for doing it is the way it connects the math and makes you kind of think through the problem, and also leads to a better understanding of inverse trig. So that ends section 4.7. These 3 videos cover